All right, let's go get ahead and get started this last hour. I have had the advantage, perhaps, of being able to see these other two presentations and have been able to remove some of the redundant slides and content. Some of the redundant stuff I've kept in just to kind of re-emphasize it. The upshot being my deck is pretty small. I'm going to be able to kind of walk you through the resources that we have up on the internet. So I'm hoping, despite the large amount of silence we've had so far, that there'll be questions that come up either through what I'm saying or what I'm showing that will help all of you get started. And we're going to have what I'm hoping is quite a bit of time for those questions. So yeah, come ready trying to think about what you're trying to do with Helix and what you're hoping or what you need clarified to make that possible. With that, let's get going. So this was already mentioned. Otto mentioned this in his presentation. Can't remember if Phil did or not, but Otto talked about the core functionality that Helix provides is the traffic cop and the postmaster. Those are great words. I feel like I should have just stolen those and put them here, but that is the core thing that Helix is doing, is providing a way to synchronize your simulators so that they are moving together through simulation time in a coordinated manner, and then allowing them to exchange data as that stepping through simulated time is happening. And Phil kind of alluded to this, and there's a question in chat related to this. The reason this is important is because if you don't do the simulation coordination, you can't do the message exchange, or at least you can't reliably do it. If you had two simulators and one was simulating the next hour and one was simulating the next week, if the simulator that's simulating a week ahead sends any kind of information to the simulator that's simulating the hour ahead, that information is right meaningless. Like it's out of context. It cannot help this simulator that's not there yet in simulated time. And if the simulator that's simulating an hour ahead takes that information and does something with it, then you're just going to get garbage out of this, right? So that's why you've got to keep the simulator synced up, and that's why that's such an essential core functionality. And it seems, I don't know, it seems really simple at the end of the day if we just say this is what Helix does. It does these two things. As you'll see later on, there's big APIs out there that it turns out there's a lot of details that get into this. Managing timing and getting your simulators to request and respond to the correct times is surprisingly tricky once you start getting into more complicated spaces. So I say that to say, if you're just getting started with Helix, this is probably where you're going to get hung up for a little while, and it's going to take you a while to get comfortable with the APIs and to feel like you can understand what you need to do to get your federates to behave properly. We've talked about these terms before. Phil just went over them. I'm going to go over them again because it's super duper important and people get kind of confused. You can see here that we have a broker. The broker manages, in some respect, the co-simulation, though, as Phil said, it does not centrally control the time. Granting, each federate is responsible for that. The interaction through the simulation is done through a core. For most people, most of the time, the co-simulations they implement, there's one core per federate, though that doesn't strictly have to be true. If you're curious, we can talk about that later. But this core is responsible for providing an interaction for the federate code that you're trying to run to the rest of the co-simulation. The federate itself, the best way I can think of to think about a federate is an instance of a simulation tool. So if you have something like OpenDSS or GridLabD or PowerWorld, those are the simulators. It is not against the rules to run 10 OpenDSSs in parallel, but they need to be distinguished from each other, right? So we would say that those are 10 federates all using OpenDSS, and they each have unique names. In this case, I'm showing Federate A, Federate B, et cetera, et cetera. The federates communicate with each other effectively through these interfaces. These are the value and message interfaces that Phil was mentioning earlier. So the connections can be established between these interfaces that allow the information to take place. Obviously, some of that information exchange or some of the details of that information exchange is actually being handled by the core and the broker and blah, blah, blah. There's details, but from the from the user perspective, for somebody who's actually using these APIs to write code with Helix, we talk about the interfaces being associated with the Federate. And I should say, just like everybody else, all the other presenters, feel free to interrupt me and just pipe up with questions. You can do like you've been doing and type in the chat, and Phil, I'm sure, will be able to answer those questions very capably. Like I said, we're gonna have lots of time. Phil talked about core types. Want to reiterate that the core is, you can think of that in some respects as kind of the message. One of the things that it does is it provides this message bus technology. 0MQ is our default core, and it's a super high reliability core. Adds overhead on top of things. It's built on top of TCP specifically, but it's a great core for most applications. If you don't have a reason to, probably don't switch from using 0MQ. TCP and UDP are just like they sound, like they use those protocols as implemented on whatever machine you're using. UDP does not guarantee delivery of messages, so it has super low overhead, but at some point, if you're using a UDP core, you got to ask yourself how important, like make sure you're doing that right, right? If you're doing co-simulation where the possibility of data loss is not that important, make sure that's true and that you're not fooling yourself. And then we have kind of some specialty cores Phil mentioned before, MPI for working in your HPC environments, IPC is shared memory, so federates that are running on the same computer can access the data they're exchanging through this shared memory interface, versus all of these other ones use a network interface, all the ones we've talked about previously, that is. So they're using the network stack. Even if you're talking to federates on the same compute node, they pretend like they're sending information over the communications network to talk between each other. IPC cuts out all of that overhead associated with the communication stack and just allows you to share information in memory. But then obviously you have to be on the same compute node. And then there's some specialty versions of the TCP and 0MQ core that use single sockets. Again, we can talk about that more later if that's important to you. Again, repeating this just because it's important. There are two main types of interfaces you'll set up, or sometimes they're called handles. There's value interfaces. You'll hear those talked about: publication, subscription, and input. Those are kind of the Helix names associated with those. Those are intended for physical values, anything that you can kind of measure, voltage, current, speed, all those kinds of things. That's a value interface. And those are persistent because things like a voltage always exist. Even if the value is 0, it is always there. There is always a voltage. You always have a height. You always have a weight. Those are values as well. That kind of information is persistent. So at any time, any federate that is subscribed to a value interface, a publication from another federate, they can just say, hey, what's the voltage right now? What's the voltage right now? What's the voltage right now? And that value may or may not ever change, but there is always a value there. The messages, by contrast, are much more like, an email or a data packet over a network, those kinds of ideas where you have more abstracted information that is being specifically sent from one federate to another. And that information generally is either sensor measurements or control signals. So if you're making a controller, there's good reasons that you might want to use message interfaces rather than value interfaces. Messages are ephemeral in the sense that once you send the message and the recipient receives it, it disappears. There's no longer a message there to be received. So you get one chance to receive that message, and then you receive it and you do whatever you're going to do with it, and it's done, right? It ceases to exist. Unlike, again, the values, right? There's always a voltage there. With messages, you may not have a message most of the simulated time steps you do. Maybe, it depends. That's the big difference between those two. And as Phil mentioned earlier, translators allow you to kind of bridge between the value and message interfaces. So you can have a message that goes from a controller and ends up at a value interface and vice versa. Yeah, just move on from there. Okay, so here is maybe, like, if you've been wondering, how do I use Helix? Hopefully this is the start. Phil went through this a little bit. I'm going to do it with some colorful blocks. If you have questions, again, please pipe up. This might be, yeah, this could be a good time to be asking those. So the first step, looking at our little flow chart here on the left, the first step that you're going to do when you, and I should step back just a moment. When I talk about you, I am talking about somebody for the purposes of this slide. I'm talking about somebody who is going to be writing a federate, or who is going to be incorporating or adding Helix support into an existing simulation tool. So for example, GridLabD is an existing simulation tool for the distribution power system. And somebody had to go in there in that big source code and add in Helix API calls so that when you want to use GridLabD in a Helix co-simulation, it works. Alternatively, and we'll get to this in another slide, you may be writing just like a controller, maybe, to control something in GridLabD, for example. And maybe you're going to write that in Python. You are going to have to use similar API calls so that your controller, which may be doing super simple stuff, it may take an input and add one to it and send that as a control signal back out, or it may be getting an input and then performing a complex optimization and sending a control signal back out. Either way, you're going to be using Helix API calls to get to where you need to be. So what we're going to be talking about here are at a high level, kind of what those API calls are doing, and then later on, as we have time, we can look at actual example federates that are implementing those APIs. So first step for a federate is you got to kind of instantiate the federate itself. So that involves, as you can kind of see with those two sub-blocks, one is setting up the interfaces, that is defining what information you want to send out and what information you want to get back. And then also configuring the timing, thinking about how often does this federate need to run, what is kind of the minimum time resolution it understands. For example, GridLabD only understands things generally that happen on a 1 second scale. If you send a control signal to it that is at a half-second step, it's not going to do anything until we reach the next one, integer 1 second to respond to. So that there are Helix APIs that allow you to do all these things to set up the interfaces, configure the timing, and then it's not shown in this block diagram, but there's as Phil mentioned previously, there's an initialization period or mode, I guess you would say, where your federate can interact with other federates kind of before simulation time 0. And then there's the main execution mode, which is when you're in simulation time 0 and further. So that's not exactly shown between the purple blocks, but once you're all set up, once you've been initialized, once everything's ready and you've entered execution mode, you make a time request. And that is, what is the next simulated time that this federate wants to simulate or has to simulate? You may have, the physics of your system may be complex enough that hey, if I don't simulate every 10 seconds, then I know the differential equations inside get hard to solve and the approximations get bad and it's no good. Or maybe like in the case of a controller, you may say, I don't have anything to do until somebody sends me a new input. So I'm going to request a time very far in the future and then let Helix tell me when somebody sends me a new input. And so I can respond to it. So you'll request a time. That's a blocking call, generally speaking. Bill said there's those asynchronous versions, but most people most of the time start out with a blocking call. And by blocking call, we just mean that code does nothing. It is sitting and waiting for Helix to respond back and say, okay, now you can simulate that time. During that blocking call, everybody else in the federation, all the other federates are doing stuff, right? And you may depend on the results of those, the simulations that those are performing, the models they're solving, to figure out what your federate is going to do. Again, like if it's a controller, you may be waiting to see what the result of the power flow solve or the optimal dispatch is, so that you can figure out what to do next. So you sit there and you wait, and Helix will return, when it's time for you to act, it'll return 2 times, or one of 2 times. It'll return the time you requested, or it will return a time earlier than that. The case in which it returns a time earlier than that is when you have, say, requested 1 hour, but one of your inputs, one of the things you're subscribing to, for example, receives a new value. And so Helix leaves it up to you, the author of the federate, to decide what you want to do in that case. Maybe you generally don't care about those new values and you do nothing. You say, you know, I actually probably nothing important is going to happen until 1 hour later. So if anybody requests, you know, sends me new data, I'm just going to ignore it. And as Phil mentioned, there's actually an option you can set that tells Helix that says, hey, I don't even wake me up. If I ask for an hour from now, that's what I want. Please don't bother me until we've reached that simulated time. So you'll get one of those 2 times back, and it's important to evaluate that time as the author of the Federate to make sure it's what you expected and figure out what to do when it's not what you asked for example. You'll then go through a process of getting any new information from your inputs or from your endpoints that are receiving messages. So the messages and values, you'll basically be getting new inputs into your model that other Federates have sent you while you've been in that blocking call. That's this kind of almost cyan block here. And then you do your simulation. That's this green box. Like for GridLab-D, this is doing all the GridLab-D stuff. This is solving the thermodynamics of house. This is solving the power flow. This is voltage regulator control actions. This is calculating the solar power output. This is calculating any inverter control changes. All those things are happening inside the block. If you're writing a new Federate, this is kind of the core of the thing you're trying to do. In some respects, you're depending on what your Federate does, most of your time may be spent in this block, and that's okay and normal, right? Not a big deal. But I say that just to kind of emphasize, most of the blocks we're showing here are about Helix. Most of the complex code could be in here, is likely to be in here, right? This is the reason you're trying to make this new Federate, is because of the neat things it's going to do in here. So you get your inputs, you use those to change your model state. These are generally boundary conditions. So that, again, using GridLab-D as an example, oftentimes an input to GridLab-D is the substation voltage that we got from a transmission system solver. So given that new voltage, what is the power flow? And GridLab-D will solve that, right? So you're getting new inputs, you're updating your model state and resolving, doing all your simulation model stuff. And then once you've solved, you send those new results back out to the rest of the Federation so that they can see the new state that you're in. And then you loop through and request your next time. So you got this loop that goes over and over again. You request time, get new inputs, resolve your model, update state, send new output state, send new model states as outputs to the rest of the Federation. And you do that over and over and over until you've simulated long enough. I've rambled here for a minute. Any questions about that?
Nothing in chat.
Oh, hi, Trevor. We can
Yeah.
still send commands to change the model inputs even if it is not in the requested time, right? If I understand it correctly.
So you're saying if I request an hour from now and I get a minute from now, you can
The
still do this?
commands. Yeah.
Is that what you're
Yeah.
saying?
If we.
Yeah.
Mhm.
Yeah, it is entirely like Helix makes no requirements on what you do. Like you could be a totally bad Federate, right? And every time you request time, you could just ignore that. You could never send an output that everybody's depending on, right? There's no kind of top functionality inside Helix that checks to see if you're doing what you should be doing. That's for better or for worse. Obviously, that means you as the Federate author have to make sure that you're doing the things that you think are most beneficial that you're trying to accomplish. Anything else right now? Okay, let's move on. So here's 2 kind of somewhat fictitious examples of how you might incorporate Helix into to make it a Federate, make it possible to be a contributor. The top part is kind of a bridge or wrapper functionality or implementation, I should say. And this can exist if there are APIs for the simulation tool that you want to use. I've made one up in this case, I call it Grid Simulator. And what we're showing here is, Python code, but you can see here at the top, I import 2 libraries, two APIs effectively. the Helix API, and the Grid Simulator API. And then I'm going to go through this loop just like you saw before. So while the time, oh, this should probably be like granted time, actually. There's a bug. You can tell this is an actual real code, is less than a max time that I've defined. I make a request, a time request. Oh, maybe not. Well, yeah. That time for whatever time I'm interested in. And again, this is a blocking call. At some point, Helix returns that and says, okay, here's the time you're working on. In this case, it looks like I'm looking for a message rather than a value interface. So I check my endpoint to see if there's a message. And there's actually an API not shown here just for simplicity where you can see, is there a message? And actually, Phil, out of curiosity, what happens if you try to get a message and there is no message there? Remember?
You get a null message object.
Okay, you get a message that has nothing useful in it. Okay, so you'll get that back. And then that's, for example, a control signal from another federate. And then using this fake tool, Grid Simulator, I say run the power flow, and here's the model object and the time we're at, and here's the control signal you need. And so this API call, run power flow, is assumed to be or must be a part of this Grid Simulator API. So you just run that and you get the power flow results, and then you take one particular power flow result out and you publish that as a demo. So this is just Python code. This Python is kind of merging together the Helix API calls and this Grid Simulator API calls. Obviously, if Grid Simulator has no API, for example, GridLabD has no API, you cannot control it in Python, then you can't do this. This only works if the simulation tool itself is providing that API. The second way you can incorporate things requires on having access to the code base. So you could, for example, we pretend that this is the Grid Simulator source code, and we include the Helix library, helixmessage.h, the header file for that library. And then we go through and we do the same things, but now we're using library calls inside the Grid Simulator source code to achieve those functionalities. So rather than writing, kind of our own wrapper around it, we have to go into the source code and figure out, okay, where exactly in the source code do I make a time request? Where do I need to get my new values, right? And so you've got to know that code base well if you're going to try to do this incorporation. So in this case, same exact step, right? We make, well, I didn't show this part up here. We make a federate. We request time. Once that time is granted, we get the message from an endpoint. We run a power flow. This run power flow is not an API call. It is a function or method inside the Grid Simulator source code. So we run that and then we get a result, and from that result, we publish values out. This is more or less, not more or less, this is how GridLabD, for example, because it doesn't have an API, the developers of GridLabD have had to go into Helix or go into their source code and using the Helix library added this functionality. So these are the two ways. If you don't have access to the source code and you don't have an API for the tool, then you need to ask somebody who does to do this work for you. As you might expect, depending on the tool, if it's a big commercial tool like PSLF, right? They may or may not be super interested in providing Helix support, and so that could be a problem. Some like as Ben said, and in many cases we've been able to find ways to get support in for those bigger tools. But if you want to do the work yourself, this is kind of the requirements. Any questions on that? Okay, so briefly thinking about if you're getting ready to incorporate Helix into an existing tool or write a new Python controller or something like that, here's some questions to think through. One, which we just went over through a lot, can you actually do the integration? Do you have source code that you know well enough, or is there an API you know well enough that you can use the Helix APIs appropriately? What programming language is being used? We support a lot of languages, but not all of them. So if the tool is written in a language or you want to use a language, you need to make sure that Helix has a language binding that we support for that. And almost all of the languages that people are using these days for our kinds of simulations at least are supported. The simulator's concept of time. This is really important to think through as, again, you're thinking about the timing and you're thinking about what you want to do in terms of incorporation. Most of the power system tools use a continuous representation of time. That means time can be any specific value in a range and that it steps through this in kind of a continuous fashion. NS3 is a great example, though, of a tool that uses a discrete representation of time in that it has no specific time that it simulates. It has instead an event queue inside, and every time a message is received or sent, events are added to this event queue to take place at specific simulated times. But there's no like, it doesn't simulate 1 second, then 2 seconds, then 3 seconds. NS3 simulates at key events. So that can be, that's important to think about as you're doing the integration. And then the last one, the use case for the integration, almost always when you integrate a tool with Helix, you will not be able to do the integration such that anybody can do anything with that tool in the future. That's very hard to do. Most of the time, what you're going to be doing is you're going to be creating an integration that is useful for maybe some large subset of those use cases, but may or may not support all of them. And that support really comes down to, are you able to write your integration in such a way that the tool can be arbitrarily configured to allow the right information to come out and go in such a way that it can work. That's hard to do, and that takes effort. So most people, most of the time, when they start doing a tool integration or they're writing a new Helix simulation tool like a controller, they're doing it for a very specific analysis they want to perform. And then later on, they realize, oh, if I could do it in this way, then maybe I could actually use this controller in a broader set of circumstances. So that's a big, complicated discussion. Again, we'll have plenty of time to talk about that if that's the case. A few other features, we've talked about most of these. Dynamic federations, you can have federates that join and leave the federation after simulation time starts. FMI support, if particularly in the building space, if you're using Modelica, Open Modelica, Modelon, I guess is what it's called now, we have a way that you can incorporate those FMIs, or FMUs, I should say, into a Helix co-simulation, which is pretty great. Queries, Phil mentioned before, you can are super useful if you want to understand the state of your federation. You can write those queries, and again, that they're not time regulated; they're asynchronous, so that's very, very useful. Co-iteration, if many people, at least initially, write their federates so that they have that loop like I showed, and the new time request they request is somewhere in future time. If your federates support it, you can actually request the same time that you're at and iterate effectively with the rest of the federates in the federation until you reach a converged state. Phil mentioned this already. We have some support for that. Command interface for sending arbitrary commands. That's something you kind of need to build support into for each federate if you want to have, if you want to make up a new command, you need to make sure that the people who send it and receive it know what that means. But that's the interface is there. You get to define kind of what the protocol, what those commands look like, and then a REST API. We won't be getting into that today. CLI, wanted to this is the exact same slide that Otto showed. I wanted to reiterate it. CLI is super convenient for launching co-simulations. Before Helix CLI existed, if I wanted to launch a federation with 3 federates, I would open 3 terminal windows and execute, well, actually 4. I would have the broker and then 1 window for each federate that I would be instantiating that federate. I would basically, this exact exec line, I would be typing into each one. And then I would sit and wait, right, till those run. CLI allows you to find this JSON that basically goes through that process of instantiating all the federates for you in your co-simulation. You can obviously make automation that writes this CLI JSON for you as part of setting up your models as part of the co-simulation. For me, the super nice thing about CLI is that the logging is handled well. So that logging from your federate is incorporated with logging from Helix, and it all gets put into one log file, and that is great. Highly, highly useful. I think that's it. Okay. There's a bunch of links. We're actually going to go to some of those links right now, but again, a quick pause for questions, and then I'm going to show you resources. Okie dokie. So let me just pull this down. So docs.helix.org is our, as the name implies, kind of our main documentation site. If you are new to Helix, this is where you should be starting if you need to learn more. If for some reason everything we've said over the past 3 hours hasn't sunk deeply into your brain and you need a refresher, this is a great resource. Some of the key features, we have what we call the user guide. This goes through, helps you not only help this orientation page, helps you understand kind of where you might need to go depending on your skill level. We have a whole page dedicated to how to install Helix, depending on what you want to do with it and where you want to use it. Good news, if you're using Python, pip install Helix is great. And then and we also go through how you might want to compile it if you need to, and installing Helix CLI, etc. So the user tutorial, we've spent a lot of time in here, and it walks you through an overview. Hey, look at those graphics. You might have seen that earlier today. Walks you through Helix and what it does. And then there is this whole list of what we are calling our fundamental topics. These are the same kinds of things we've been talking about now. Walks you through each one of these pages, talks about what these concepts mean. And then here at the bottom of many of these pages, scroll, 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 you will find, oh, not on this one. Take that back. I forgot how this was structured. So this walks you through these concepts. So that you can, basically what we've been already talking about today. In parallel with that, we have these Helix examples. I'll show you this as a separate repository here in a minute, but these examples are all written in Python. We have pages for each of these examples that we support right now. And it shows you how the federates are being defined and set up, shows you what happens when, let me skip ahead. Yeah, here's the base one. So it shows you how these federates, what exactly these federates do, how they interact with each other. And then at the bottom of the page, here's what you type to run it, and these are the results you should get. And we've got a whole raft of these. We've got what we call the fundamental examples, which cover the topics that are roughly covered in the user tutorial, and then the advanced examples that talk about some of the more advanced features of Helix. Like I said, these are all stored in our Helix examples repository. So you can just clone in this example, this repository. Here's the user guide examples. We've got them all sorted out, including the ones that we haven't sorted yet. And you can look through here and see, look, if you wanted to, run a dynamic federation, actually that one may not work right now. We got them, always got things that we're trying to improve on that. But if you want to run an iterative example to show how you can reach convergence or get closer to convergence in your federation, including, I think, yeah, the link back. So this is great. If you are trying to see how federates actually work or trying to look for how a specific feature is implemented, this examples repository is extremely, extremely useful. Also useful in here. So there's the examples, the user guide. I didn't even click over here. Our advanced topics continues to grow. There are tons of different details like broker hierarchies that we've talked about. Iteration, which we just mentioned, how to implement callbacks if you want to do that. There's many features that we have that we want people to know about and be able to use. Another way of kind of looking at this or trying to understand the features is we do have our references. So we have for example, our API references. Again, I use Python a lot for this. Even if you don't, well, I should say this. Basically everything except the C++ API is the same API or extremely similar. We have the language binding support that we provide with Python and Helix and Julia and C is all based on the C API. So the API names that you will see in C are the same as what you'll see in Python, and the signatures, the parameter lists are extremely similar. We've done some fancier things, for example, in Python to make it a little bit easier. So sometimes the signatures are slightly different, but if I'm trying to understand, is there an API out there that does what I need to do? The Python API site is fantastic. So you can go up here and you can type Helix, Federate, request, let's see, request time iterative, right? Click here, jumps down there, and it shows you the parameters that you need to include and the definitions for that API. And as you can kind of just see scrolling through here, there are a ton of federates, or excuse me, a ton of API calls, many more than you would than you might expect. As Adil mentioned, there is kind of what we're calling the Pythonic API. So it basically wraps the C calls inside data structures or APIs, and maybe it's just a better way to think about it. Classes essentially that make this a lot. If you're used to using Python stuff, this probably looks a lot more like Python than some of the other code you'll see. So there's some examples of how to do certain things with the Pythonic API. This is just kind of a short sample, an example. There's much more of the API that is implemented in this Pythonic way than is shown here. Clicking back over here. So looking at the API itself and just kind of scrolling through that is useful. The other thing, and Phil mentioned this earlier, we have what we call the configuration options reference. This is a monster page, and it tries to be exhaustive with all the different features, to some extent APIs and configurations you can make with your federate. So there's two ways to do configuration in Helix. You can either do it through a JSON, which you see here, and you basically, there's an API that you call that says, build me a federate based on what's in that JSON. One line command, done. Alternatively, if you want to do something fancier or you need some kind of dynamic configuration for your federate, or maybe you just prefer, you can use APIs. There's APIs that allow you to define every option that you see here. So the two are completely interchangeable, or at least they're intended to be. If they're not, that's a bug. And you can see here there are a ton of different options and ways that the configuration can take place. So in some respects, this page is in a small way kind of like the feature list for Helix. If you want to know about if you can do a certain thing, look to see if it's an option you can configure, look to see what API is there. So you can look at this, you can look at the API listing like for the Python Federate or the Python or Julia or MATLAB, whatever you're using. And this kind of shows you just, there's a ton of options. There's a ton of things you can do. Early on, I'd recommend looking at these timing options since timing is always a challenge when you're just getting started. You can see in here, and you can see, for example, there's this period option, which you can define in the JSON as just period and then provide an API. And then let's see if this works right now. Nope, it doesn't. Need to update that link. I think the Julia one does. I just updated that. It goes to the generic page. Okay, well, there's work for me to do there. But you can, alternatively to setting this again in the JSON, config JSON, you can call this API with this value to define the period property itself. So again, lots of different options, lots of things you can mess with here. And again, timing is a common complication. So this is a good one to get familiar with early on. I feel like I've just kind of carpet bombed you with information, but are there any other questions? Okay, well, let's just look at some Federate code briefly. This will probably be the last thing I do as kind of the formal instruction. If there are any other questions, we can address them then. Actually, I don't want to go to the user guide examples. So we have this what we call the unmaintained folder, which means these examples worked at one time, and we may or may not have updated them to work correctly now. There's one that I developed for a recent presentation, this Python demo. It's very similar to the user guide examples, but a lot of the it's been stripped down, so it's a little bit simpler to see what's going on. And let's go back to the documentation page so we can look at is it here? Gosh, I can't even remember now. Yes, this is the example that we're showing. This is again very similar to what's in the user guide example. In the user guide example, we have 5 EVs and 5 chargers that are interacting. This Python example is just one of each. So we can, here, I'm going to open these up, and heck, let's open up the runner as well. So here's the code. Again, this is up there. You can download this. You can play around with it. I believe it's working. It was working a few weeks ago. I haven't run it super recently. You know, kind of some boilerplate stuff up there. I write this. I include this destroy federate method or function in all of my federates just to help avoid some persnickety warnings. You can look at that there, or you can ask questions about it. And then I am doing my simulator setup stuff. So these are all parameters. Ideally, these would not be hard coded. They would be passed in some way, you know, through some kind of configuration file or command line options or whatever. Doesn't really matter. And then, so this is an example of doing configuration via the API. So we create this federate info object that's going to store all the information about the federate we want to use. And then you can see right down here, we call create a value federate using that federate info. So we go through everything in between these two lines is just setting up options. We tell it what core we want to use. We tell it, you know, there's some particular properties we want to set, et cetera, et cetera. Create the federate. And then after the federate is created, we create the publication and subscription and interfaces. Again, Helix federate register publication, Helix federate register subscription. These are the exact same API calls in C, and Julia, in MATLAB. They all have the same name. They all have the same signatures. Again, the only difference, the C one has an error object or an error pointer you can provide at the end. So if you need an error message, it comes back. But everything else is identical about these. They're all based on the C shared library. So we create
I
the
would
interfaces.
add that the other languages generate exceptions instead of using that error object, which C does not have.
Yes, good point. Thank you. So in this case, you can see just by the fancy name I've given this federate, this is the battery federate, is going to publish a current and it's going to receive a voltage. So publishing a current, subscribing to a voltage. But the voltage, as you might guess, is going to come from the charger federate. So we set those up. The publication we define, give it a name and say it's a data type double and has units amps. And then the subscription, we say it's going to come from charger and it's going to be called voltage and its units are volts. And actually, we can just probably jump right over here and confirm that reality is true. Same thing, look at this, voltage. It's what we're subscribing to here. And this the charger slash indicates it's coming from charger and it's called voltage. And the data type volts and amps. And you could do different meaningful units on those, and Helix could handle the conversion, which is to say you can publish in one unit and subscribe in a different unit, and Helix takes care of that without you knowing. And then similarly, this federate, the charger federate, is subscribing to the current, and this federate, the battery, is publishing that out. So very, very simple interaction, right? These two, just like this. One sends out a voltage, one sends out the current. They each rely on the other. Once that interface is set up, we enter initialization. In this case, we just use the initialization mode to send out a initial value, something prior to t equals simulated time equals 0. So you can see right here, the initial current is going to be sent out is 0. And then the initial voltage, if we look here, V init, where did that go? Is 5 volts in this case. Very powerful EV battery, apparently. And then after initialization, so the Federates exchange that initial information, and from that they can, if they need to, they can do some kind of initial solve of their models. And then we entered the execution mode, and this is just like I was showing you on the slides. We request a time, we're going to get granted a time. We go get that voltage that was provided to us by the charger. And then, yeah, this is the initial execution before time starts. So here's the main, like it says, main co-simulation loop. We did this to basically get the values sent during initialization so that we have them when we go through this loop the first time, as you can see. So we set up the initial state of charge as well. Yeah, we don't do anything like that. Okay. And then again, the main, here we go, for reals this time, the main loop. So this is this while loop, we're gonna look as long as we're less than the simulated time, or I added in this extra condition, if the voltage, as long as the voltage is greater than 0. If the voltage goes to 0, that means we're not gonna be charging anymore, and effectively we're done. So while we're inside that condition, we request a time. In this case, we're gonna manually calculate the requested time. We request it, and I've had this logging stuff so you can see we were actually requesting it. Here's the time we got back. We get the inputs just like I was talking about before, as long as the voltage is greater than 0. This is like the battery model, basically. These 3 lines might be the entire battery model, right? So I interpolate, I just assume I've made up this stupid relationship between resistance and charging current. And based on the current state of charge, we can find that resistance, and then we receive the voltage from the charger divided by that resistance, gives us the charging current. You can also calculate the amount of charge that was added to the battery, do all that kind of stuff. And then all we send back out is that charging current that we had. Send that back to the charger. And that's the loop. That's the loop until we run out of time or until our voltage goes to 0. And as soon as our voltage goes to 0, we drop out of this destroy Federate. That's this thing up here at the top. We can talk about that if anybody cares, and then we're done. Right, so that's the loop over and over and over again. Similarly, from the charger side, I think it's even simpler because I don't think the charger. Oh yeah, no, there is. The charger is trying to, in this case, is trying to regulate the charging current to a specific value. So it's going to change the voltage as a function of the current, charging current. Same kind of thing. Request the time as long as we're not fully charged. Request the time, get the charging current. If the current is above the terminal charging current, then we change it. This is an internal function that I defined. Where is it? Set charging current right here. So you can see if the current is too high, we reduce the voltage a little bit. If the current is too low, we increase the voltage a little bit up to Vmax, an arbitrarily defined parameter. Again, super simple controller, not intended to be good. It probably oscillates in some conditions, not a big deal. So we set the charging current, and then we send the output. Here's the new voltage based on the charging current this charger has received. And again, do this over and over and over until the battery is fully charged or we run out of time. And once it's fully charged, we destroy the Federate and we're done. Questions on any of that? Any details you saw in looking at that you want clarification on? Okie dokie. Well, and then as promised in some respects, the this is the runner JSON file. These are super simple to put together. You can copy and paste this one, and all you generally need to change is what is the command I need to run to launch my Federate. You know, what do you type in the terminal to actually get this started? And you do one of these blocks for each of your Federates, and then you can give it a name up here. This is a little bit confusing because there's actually a name you can. This doesn't have to be the same as the name in that you give your Federate via the API. or via the configuration. So you can accidentally confuse yourself. I won't comment whether that's happened or not to me. But the nice thing, as I said before, all of my, for example, my logger commands right here will show up in a file called charger.log. Super convenient. Also, all of the Helix library log messages, you can turn, set the logging level for Helix. I bet I don't know if I set that in this one. It's probably just default. But that can generate helpful debugging information depending on what you want. So you just, this Federate is just a list object, or a list, I should say, not an object, and it contains these object blocks, and you just define each Federate. The broker true command here just means I'm going to not call out my broker. Generally, if you're just running a few Federates on one computer, this is a handy way to not have to define a broker block or have any of your Federates generate a broker for you. This just takes care of it. It basically just looks and sees how many entries are there in this Federates listing, and then says, okay, I need to make a broker that will handle, in this case, 2 Federates. Done. Super straightforward. Yeah, and then you can running this example is as simple as Helix run, and then you path equals, and you hand it that runner file, and it takes care of launching it.
Trevor, there's a question in chat. When you have a large number of Federates, how do you create the runner file? Do you do it manually, or is there a way to do it automatically?
Yeah, the generally when we're running large code simulations, and large, sometimes that's like 6, right? At some point you get tired of copying and pasting. That's kind of up to you. Usually we write our own tools to generate the runner file. One of the co-simulation based projects as a part of, we were generating many hundred Federates, and as part of setting up our models and getting the data files in the right places and all that kind of stuff, we had functionality that would generate this runner file for us. There's no built-in Helix API to do that for you. The nice thing, at least in Python, that's because it's a JSON, like you can just make a dictionary. You could, yeah, it's super simple, right? Make a dictionary, JSON dump, send it to a file, you're done. So it's doesn't have to be complicated. And I should say, usually we would do that at the same time as let me click back over to our user guide examples. Usually we would make that runner file at the same time that we are making the configuration files, such as this, because we would know at that point how many Federates there are. These would also be automatically generated by that same Python script. And then we would dump out that runner file as well. We are close to the top of the hour. Any other questions?
Could you show how you would run this example with the Helix CLI?
I was afraid you were going to ask that. Yes, I will take my fate into my own hands and actually try to run an example simultaneously, or not simultaneously, spontaneously. Okay. One moment. So here is, I'm a big believer in color. So this is Helix Blue. I've already installed Helix. We can check that by, or you can do it that way, but probably more useful. We can ask the broker for its version to confirm it exists. Yes, so I'm using Helix 4.0. I've set up a Conda environment. So where are we? Yeah, td-helix examples. Now let's do one of the user guide examples. Until default. Okay. So let me also confirm that I've got the CLI installed. I do. So Helix run -- path equals fundamental default runner.json. Okay, last chance for any bets on whether I've actually done this right. Okay, here we go. So you can see right now it added a broker for me, and this is the command it actually made, so that's good. These are the 3 processes that are running right now, as it says. Sit here for a minute. Hey, there we go. Look at this. These are the 2 graphs that get created, and let's just because I'm here and I'm, feeling like things are actually going well. This is in the examples folder. Yeah, look, there they are. There are those 2 graphs. So here, let me move that out of the way. I feel so proud. There's 5 minutes left. Nothing is broken. That is amazing. Okay. Then it says things are done and nothing broke. So let's now I'm really feeling it, right? Let me open up the source code on that. Let's add in an error just so you can see how things look when things don't work right. Helix examples. Here's a guide. Fundamental default. Okay. So here's the source code. If we go to battery.py, and what can we do here? Fed9. Fed9 does not exist. This is not going to work well. Oh, I should have, yeah, this is a good example actually. So here's, instead of using the APIs, when you use a configuration file, this is all it takes to make the Federate. Instead of those whatever 5 or 10 or whatever lines in the API, you can do it all with config. So I define my Federate that's created by this API as Fed, not Fed9. So if we try this again, it will say there's a problem as expected, and it dumps out to console, and we can see battery.log, the same message that was dumped out there. Charger.log, this is probably from the old run, yeah, all the detailed information. So we can go back in, obviously fix that. Run it again and it will run. Oh, did I save? Did I see me save? I did save. Okay, good. Phew. Anything else? Okay, well, I'll pop this up here. There's my email address. We can, yeah, as mentioned, the Gitter channel is great for real-time feedback. You can file bugs, you can see the discussions that are happening, and then these are the user guide links themselves. So thank you all for coming.
All right, if there's any other questions or topics, we'll stick around for a few more minutes yet.